Okay, this new chapter is called Vector Spaces. Now, you will find as you read this chapter that it seems very much like deja vu. This chapter is very similar to the chapter on vectors. It also talks about vector operations and vector properties. Now, you might wonder, why are we doing this all over again? Well, the reason is that vectors are not vectors. What do I mean by that? The vectors that we saw before were column vectors. And we've done a lot with column vectors. It turns out that there are other things that we can also call vectors. So we're going to generalize the properties that we saw for column vectors to apply to other situations. This idea of vector is not just something that applies to column vectors, but it applies to many situations. For instance, the set of functions is a set of vectors. And we'll see that later on. So this is something that's often done in mathematics, is you take a mathematical structure, such as in this case column vectors, and you investigate its properties. Then you find out that there are many other things that share the same properties. So that's actually what's going on here. As I said, this will seem like a lot of repetition. I hope that this explains why we're repeating what we've done already. We're trying to reinterpret the results that we already have. All right, so we're going to, I can say we're going to abstractify the notion of vector. Now, we had properties of vectors before. Here we're just going to list those properties and say that anything that satisfies these properties is a space of vectors. So I'm not going to talk about these properties in detail. We saw all of these properties for column vectors. Additive closure, sum of two column vectors is a column vector. Scalar closure, the scalar multiple of a column vector is a column vector. Now, we're going to say that any set that has an operation, which we call plus, and that has a scalar multiplication that satisfies all these properties, we're going to call this a vector space. So just tick all these off. Commutativity we saw before, additive associativity, zero vector, additive inverse, scalar multiplicative associativity, distributive vector addition, distributive scalar addition, the one constant. So the objects in V are called vectors no matter what else they might really be. Okay, so this is the important point, and we will see examples later on. Okay, these are called axioms. These are things that we assume to be true. Now, what you do in mathematics is you start out with axioms and you prove things from them. When you start out proving, usually you have a specific example in mind. But then when you generalize, you refer only to the properties that characterize that object. Okay, and he's also emphasizing that these objects can be anything, but we'll call them vectors. Okay. The other thing that's generalized here is the idea of what a scalar is. Before, we used scalars to be complex numbers, but in fact we can choose other types of scalars. In particular, often the real numbers are chosen as scalars. But there are other possibilities as well. We probably won't go into that in this class, but just to be aware that that's true. All right, so this discussion, as he says, may seem a little bit strange or not very clear, but as we go on, I think you'll see what's going on here. So let's look at some examples of vector spaces. First example is the vector space Cm. Okay, the column vectors with m components. Now, we don't really need to go through this because this was our canonical example where we got the idea of vector space to begin with. All right. Next example is the vector space of matrices. Now, we saw in the matrix chapter that we were able to do a lot of things with matrices that we did with vectors. And the reason this is that matrices also satisfy all of these vector properties. Now, notice that matrix have multiplication and vectors don't. That particular property of multiplication isn't a part of vector space properties. That's an additional property that matrices have. Okay. All right, now here's something new that we haven't seen before. The set of polynomials is also a vector space. Pn denotes the set of all polynomials of degree n or less. What is the degree? The degree is the highest power of the variable appearing in the polynomial. All right, so for example, if we have polynomials in the variable x with coefficients that are complex numbers, this is what a polynomial looks like. Okay, you have the constant term a plus the linear term a1x plus the quadratic term plus a2x squared and so on. You have, actually you can see you have n plus 1 terms in a polynomial of degree n. Okay, because there's a constant term. You can see that, for instance, if n is equal to 2, you'd have the constant term, the linear term, and the quadratic term. There's actually 3 terms in the polynomial. And we know how to do arithmetic with polynomials. We know how to add polynomials. Okay? We also know how to multiply polynomials by a constant. Now it's true we also know how to multiply 2 different polynomials together, but we're not interested in that aspect at this point. We're only interested in addition of polynomials and multiplication of polynomials by constants. Now there are other properties that you can think about. For instance, what is the 0 vector in this space of polynomials? Well, it's the 0 polynomial. What's the additive inverse of a polynomial? Well, it's the same polynomial where you change the sign of every coefficient. Okay? And you can go through and do all of these properties, associativity and so on. All these properties follow from the usual arithmetic of polynomials. Okay? So that's a new example of a vector space, something that has the same properties that we saw hold for column vectors and for matrices. All right, here's another new example, the vector space of infinite sequences. Well, we're getting even a little bit weirder, okay? So you've seen infinite sequences in calculus, and it's a sequence of numbers. For instance, here's an infinite sequence, 1, 1/2, 1/3, 1/4, ... The general term is 1 over n. Okay, so that's one example of an infinite sequence. Okay, we're not writing in set brackets, but in brackets like that. Now there are many, many other examples of infinite sequences. They don't all have to go to 0. They're just a set of infinite numbers. Another infinite sequence would be 1, 2, 3, 4, and the nth term would be n. That's another infinite sequence. Okay. Right. Now we know what it means for 2 infinite sequences to be equal. All of their terms must be equal. We know what it means to add infinite sequences. We add them term by term. We know what it means to multiply an infinite sequence by a scalar number. It's multiply each term by the scalar. Okay, so infinite sequences is another example of a vector space. You could go through and verify all the properties that are characteristic of a vector space. They hold for infinite sequences. Okay, so now another example, the vector space of functions. This is what I mentioned earlier. Take any set at all, and take the set of all possible functions from that set to the complex numbers. Okay? We know what it means for 2 functions to be equal. It means they have to agree on every element of the domain. They must give the same output for the same input. We know what it means to add functions because the functions take values in the complex numbers. So to add functions, you just add the outputs for the 2 functions. We know what it means to multiply a function by a constant. We just take the output and multiply it by that constant. Okay? So we have all our operations, and again, we could go through and verify all of the properties that we showed before. This set is a vector space with the operation function addition and scalar multiplication. All right, here's another example. The Singleton vector space. Just take one vector space. A vector space with one element. Now it turns out that this one element you could think of as the 0 vector, because if it has only one element and it has to have the 0 vector, then this one element must be the 0 vector. So if you think of z as the 0 vector, this doesn't seem so strange. Okay, so there is a possibility of a one element vector space. All right, now there's this thing called the crazy vector space. What he's done here is he's defined a new operation plus. This is a new definition for this symbol. And this symbol applies for this set C of pairs of complex numbers. Okay, so I'm not going to go through this in detail, but suffice it to say that you can define a set, define an operation, whatever you want, and call it plus, and you define a scalar multiplication, and then as long as all of the properties are satisfied, then this set with these operations forms a vector space. Okay. So he went through and verified these properties in detail. You can go through and read that. Okay, I'm going to stop here and we'll go on with the next video.